So next order of business, we have our dielectrics. So this is a way to soup up the performance of a capacitor. Okay? This is a way to make it better. Every capacitor that you will use in lab undoubtedly has one of these. Okay? What is it? So let's say I have a capacitor that I've charged up, like so. What I'm going to do is I'm going to put a filling in this sandwich. That is my dielectric. Dielectric, which really is just an insulator. In fact, some people use the term insulator and dielectric interchangeably. Okay? I like to think of an insulator as just a general thing, and a dielectric is when you're using an insulator for this purpose. Okay? So what does this accomplish? Well, first of all, I guess I should mention, why don't you want that thing to be a conductor? That's fairly obvious, right? If you put a conductor in there, then you would just ruin the capacitor because the pluses could flow across and combine with the minuses. You've deleted your ability to store charge and energy by putting a conductor in there. So, what does an insulator do? Well, let me remind you that just because it's an insulator doesn't mean nothing happens. We still have that ability for partial shielding, right? So if we have that the electric field of the plates looks like this, the material will charge polarize. They'll have the pluses, let's see, the minuses want to go upstream, so they'll be like this, and the pluses will be downstream, so they'll want to go like this. You guys remember this, partial shielding? Okay. It doesn't look like we did before. I think before it looked like this, right? We had the external field, and then we had an insulator with charge polarization look like this. It just looks a little different now, but it's basically the same idea, right? And this creates what we call E-induced, right? So if I draw it here on the side, we have E external. That's by the plates. When I say external, of course, I mean external to this hunk of insulator. I have E induced. And this is where I can remind you that, of course, the whole idea of an insulator is that you can't get perfect shielding. You can get just partial shielding. So if you combine these two, you'll get E net, which looks like this. It's in the original direction, right? It's in the original direction of the external field, just a little bit weaker, right? So we call this partial shielding. We found no practical use for this at the time when we were doing homework too. I just pointed it out. Now we're going to find that there's a very practical application to this. Okay? So if you had perfect shielding of between conductors to think for getting inside something metal in a lightning storm or something like that, now we find partial shielding has a use too. Because this is going to improve the performance of the capacitor. Now it may be not very obvious why this improves the performance, so we're going to have to go through it step by step. Okay. So the first step I want to do is just establish my values. Okay, so I want to establish, this is the after the cap has gotten charged, but before I bring the dielectric around, before I insert it. So ironically, even though it would take me a long time to charge it perfectly, this is my starting point for my discussion now. So I want to talk about the charge in the capacitor and the voltage. I want to talk about the capacitance itself. Let me make sure I get everything on my list. I want to talk about, let's see, electric field. Sorry, these aren't going to be in the best order, but they're all going to be there. So this is going to be E net. And talk about potential energy. And I'll give them just, Q naught, B naught, C naught, E naught, and PE naught. Those are the values that I'm going to jump off from, okay? So the next stage I'm going to look at is the battery is still disconnected. So I've removed the capacitor from its charging battery, but now I'm going to insert the dielectric. Okay? So one of the things I've just mentioned is the fact that the net electric field will be reduced, right? So that's the partial shielding, right? So I have to tell you how that shielding is quantified, okay? So the way that we quantify this is that you might say, well, can we just say how much E induces, how much we subtract? We could do it that way, but it turns out to be more convenient instead of talking about how much is subtracted from it, by what factor is it changed. So we go E net is equal to E external divided by kappa, okay? Where kappa is called the dielectric constant of the material. Dielectric constant of the material. It's a unitless number, it's just a divider on how much we're reducing the electric field by. There's a table of them on your formula sheet. So for instance, if a material has a dielectric constant, well first of all, I guess I should say that it's 1 for nothing, right, for a vacuum. But it's bigger than 1 for everything else. Which means, of course, that we're dividing by a number bigger than 1, which means we're reducing the field. So for instance, if you have a dielectric constant of 3, that means that E net is 1/3 of what it used to be, right? If we have a dielectric constant of 100, it means that the net electric field is only 1/100th of what it used to be. It's a way of quantifying the partial shielding. And it's just doing it as a divider, okay? It's telling you how much you're dividing the field by, okay? Does that make sense? So if we go over here, the net electric field is divided by kappa, is reduced, okay? But now what we're going to do is we're going to see that that trickles through to having effects on all of the other things, okay? The first of which is this. We of course talked about the relationship between electric field and voltage, and we've long since talked about it like this. And of course, I'm not changing D, I'm not changing the distance between the plates, which means that these two go together. the electric field strength and the voltage drop across the capacitor are tied together. So if I've reduced the electric field between the plates, I've also reduced the voltage. If I reduce, they're directly proportional, which means that if I've reduced the electric field by kappa, I'll also have reduced the voltage by kappa. So, what's going on here? For instance, I could have charged this capacitor originally with a 9-volt battery, which means that the voltage drop across is 9 volts. But then I could put in a kappa value of 2 and reduce the voltage difference to 4.5 volts. How is the voltage difference reduced? Well, just think about it. If I were to suddenly discharge this with the dielectric in there, like this, it wouldn't be nearly as excited to discharge. Yes, this positive charge wants to get away from other positive charges on this plate, but not as badly. It's like, oh, there are these negative charges around. I kind of like those, right? You might ask, why doesn't it flow directly onto those? Remember that these are bound, right? They're hanging out nearby, but they're not actually really a part of the plates, right? They haven't joined the plates. Those are bound charges, so they're just kind of hanging out nearby. But this positive charge in this plate is not going to be as excited to get off now. But when it flows across here, to get to this big store of negatives, it's not going to be as excited to join that because there are positive charges near there too, right? So it'll still flow, but not as excitedly. So that's why we say that the energetic motivation to go from one plate to the other is not as big, right? We've gone from 9 volts motivation to, if we put in a kappa of 2, it's only 4.5 volts now. Okay? So, this seems like it's not a good thing. Okay, we've reduced the desire of the charge to do this, but we're going to find, of course, we haven't finished yet, we're going to find that there's some advantages here. Now, as far as the charge goes, the charge on the plates, can anyone see, how does inserting the dielectric affect the charge that's on the plates themselves? It doesn't, right? We have these isolated islands of charge, right? We've charged the capacitor up, we've disconnected the battery, so there's no on-ramp, no off-ramp, right? It's completely isolated. So the amount of charge is the same. We've just reduced the voltage difference between the plates, but the amount of charge actually on the plates, right? We're not counting the red charge here. We're not counting the bound charge, because that's not actually accessible charge. It's charges on the insulator. Okay, so let's find out about the capacitance. Well, of course, just like you can always relate these two, E equals V over D, you can always relate these three by C equals Q over V, right? So once you know about two of them, you can find out about the third. So let's take a look. Well, initially the capacitance was Q naught over V naught. It's a reflection of how much charge you can store per volt. Now, if we look at the new capacitance, if that is going to be our definition of capacitance, right? It's how much charge we can store per volt of effort. But now we have the same charge, but with less voltage. What is that going to do to the capacitance? It's going to be more. So we're storing the same amount of charge with less effort. Which you might rightly claim, this seems like a real technical loophole, right? What do you mean we're storing the same amount of charge with less effort? It's like a cheat, because we actually use the same amount of effort to charge it, but then we put in the dielectric afterwards to reduce the voltage difference, right? But if we're going to follow the letter of the law here, we do have an improved capacitance. And in fact, if this is reduced by kappa, then that kappa will flip up, and we've improved the capacitance by kappa. And by the way, as we mentioned, capacitance is a measure of the physical properties. So now we've actually changed the physical property of the capacitor by putting something in it. And so as long as it's in there, the capacitance will be improved. Okay? So the formula for capacitance really should be kappa times what the capacitance would be without the dielectric material. If you want, you can put in the parallel plate formula. So this is kind of your complete formula for calculating capacitance based on physical properties. You need to know the plate areas, you need to know the separation, and then you also need to know kappa, which is what is the material that is between the plates. Those are the physical properties that go into figuring out kappa. Okay? And as long as this dielectric is in here, then that should be included in the calculation of capacitance. Okay? So, seems like the capacitance is improved on the technicality. We haven't really accomplished very much, and when we go to the potential energy, you'll really see that it seems like we haven't. This is kind of pointless. Let me do that next. So I'll pick one of my potential energy formulas. I suppose 1/2. Let's do which one I want to do. I guess I'll do 1/2 QV. Remember, there's 3 forms. I'll pick whichever one seems the most instructive. If we have the same exact amount of charge stored, but at less voltage, that tells us we have what? What happens to the potential energy? It's less. We've stored less energy now. Because we have the exact same amount of charge carriers, but we have less energy per charge carrier. So we have, that's Q and V. So that should lead to less energy, right? Overall. The capacitor plates are isolated islands of charge, so there's no way to get on or off. So the amount of charges is the same. We just talked about the fact that we have these guys that are not a lot less excited to get off one plate to the other. The energy motivation has been reduced because of this partial shielding. So if we have the same number of charges, each stores less energy per charge, we're going to get less potential energy. So if Q is the same, V we already know is reduced by kappa. V is directly proportional to PE. This is going to be reduced by kappa as well. So we really, of course, look at this and go, what? Why is this better? We're not storing any more charge than we used to. It's the same amount of charge. We've reduced the voltage difference. We've reduced the amount of energy stored. This seems like it's not an improvement, right? And it isn't yet, but we haven't fully leveraged the situation. We're going to do something else now. What we're going to do is we're going to reconnect the battery. Okay? We're going to reconnect the battery and see what happens. Actually, before I go through that, are there any questions? I'm not belaboring how these factors are coming up. I hope that you guys can just do it by proportionalities or can kind of see how that's going. So here's what happens. When you connect so let's say we had that 9-volt battery that we used to fully charge this thing up to 9 volts. We take it away, we put in this dielectric that may reduce the voltage to whatever kappa is, 1/2, might be 1/3, kappa might be 2 or 3 or 100, and that reduces the voltage to 1/2 or 1/3 or 100th of what it used to be, right? So for instance, let's say we had a 9-volt battery, right? We use that to charge it up. Plus Q naught minus Q naught. Then we disconnected that battery and we just have the capacitor. it has plus Q naught minus Q naught. Then we insert dielectric. Let's say kappa equals, I don't know, let's make it, what's an easy number? I guess 3? Yeah. Let me do the 9 volts instead of, let me do it 12 volts. Let's see, my charging battery is 12 volts. And I put in a kappa of 3. Okay? So what's my new voltage drop after that? It's 4 volts. The partial shielding has reduced the voltage difference to 4 volts. And that's the situation we're at currently, but then, what do you think if we rehook up the battery, the 12 volt battery, and hook it up to something that's 4 volts? It says, what are you doing? I just charged it up to 12 volts. Now you've been consorting with these dielectrics and your voltage way down. What does it do?
It wants to charge it more.
It wants to charge it more to get it back up to 12, right? So that's what it does. Okay? So when we reconnect it, we'll bring it up to back to 12 volts. 4 volts back up to 12 volts, right? Get the dielectric in there. So the voltage comes back up. That's forced by the battery, right? The battery's going to insist. But the only way it can bring it up from 4 volts back up to 12 volts is by putting more charge on there, right? So more charge will flow, and now it's going to look like this. Which, by the way, that amount of charge could never have been put on there at first. Remember, it filled it up, right? It got it up to 12 volts here at the beginning, and that's as much charge as it took to get it up to 12 volts, right? It can never have put the amount of charge on that we're seeing now. We get to cram that much more charge on there because the suppressive effects on the voltage of the dielectric means that the battery has to push that much more charge on there to get it back up. Does that make sense? So now we get even more charge than before. And now we're talking. This seems like it's a useful property, of course, to be able to get a lot more charge on there than you would have. So now we're not just letting the partial shielding suppress the current situation. We're letting the partial shielding suppress so that we can then recover the original voltage with more charge. So let's go and figure out the amount. If we look at good old C equals QV, now we can invert that to Q equals V times C, or C times V. Well, now we have to go back up to the same voltage, back up to that original one, but with an increased capacitance. Remember, the dielectric is still in there. So what happens with the charge? It increases. In fact, if V is V naught, back to the original, but the capacitance is improved by kappa, the charge will be improved. Now we're talking. Okay? Oh, and I guess I should copy this. This is still the same thing because the dielectric is still in there. So now we're able to get more charge on the plates by this battery. Okay? Let's figure out what happens with the rest. Well, if the voltage goes back up to the original, then so does the net electric field. You might ask, if you have all this charge, doesn't that cause a larger electric field? Sure. But remember what we're talking about here is the net. It's the induced thing that brings it back down. So now we have a ton of charges, which causes a massive external field, very large external field, but then the induced one brings it back down to the original field that you would have had in the first place. The same one that you would have had here, E naught. Okay? So you have more charges causing a gigantic external field, causing a gigantic voltage drop. The battery would never have been able to get it up to that voltage before, but the suppression of the electric field by the induced and the suppression of the voltage that goes along with it brings back down to the original amount of electric field and voltage. Okay? In fact, this might be a good time to ask, what would happen if I yanked out the dielectric right at this moment? What would happen to the voltage drop across the plates without that suppression help? It would spike way up. The voltage drop across here would actually be, what would that be? It'd be like 36 volts. Or what was my kappa? Yeah, 36 volts. You never would have been able to get a capacitor charged at 36 volts with a 12 volt battery. And in fact, what would happen if it was 36 volts now? Is that going to just sit there? No. Where's the extra charge going to go? It goes back to the battery and we go back to this, right? So if we pull the dielectric out, we don't get to keep all that charge, right? Okay? The only reason we get to have that much charge without having all the voltage that would normally come with it is because of the suppressive effects of the dielectrics, right? That's what allows us to get on all of this charge while still being at the same voltage and electric field overall that we were at the beginning. So we're using these suppressive effects for good use, okay? Does that make sense? Okay, and then finally we should go back and analyze the potential energy. PE equals 1/2 QV. We have the same voltage as before. So the same energy per charge, that's what voltage is. But we have way more of them, right? We have more charge. More number of charges. So what's going to be true of the total energy stored? It's going to increase. We have more charges, each carrying the same amount of energy, so we're going to have more overall energy. So this is going to increase. And again, because these two are linearly proportional, whatever factor Q is affected by, PE will be affected by. So now we're talking. We increase the energy, right? So now, if we compare the beginning, at the beginning, by the time we've charged up to this voltage, we have so and so much charge and so much energy. Now, at that same voltage, we get much more charge and much more energy, right? So now you can see why the dielectric is useful, okay? So dielectrics allow more charge and more potential energy to be stored at a given voltage. And I should tell you, of course, while this step, this kind of three-step thing was hopefully instructive, in reality, you don't, of course, charge a capacitor, disconnect it, put in a dielectric, and then put it back, okay? The dielectric's always in there. It's permanently built in. And you go straight up to these values, okay? blissfully unaware that the amount of charge and the amount of energy you're storing are far greater than they would be if that dielectric weren't in there, okay? So when you see capacitances on the, nano up to micro to millifarads and higher, those are really good dielectrics in there that are allowing you to get that high of a capacitance, okay? Now, why is this desirable? More charge and more potential energy at a given voltage. Well, I can kind of talk about this in terms of rechargeable batteries. They're very similar to capacitors, though not quite. But if you think about trying to design like a rechargeable battery, right? You work at Duracell or Energizer, one of these companies, right? You're trying to create the best 9-volt battery you can, right? But it's got to be 9 volts. You can't say, oh, you want a best 9-volt battery you could possibly have. Here's a 1,000-volt battery. You don't want to connect a 1,000-volt battery to something that only expects 9 volts. It's going to draw way too much current and probably dissipate too much power and damage the thing, right? So you're restricted in a given voltage, right? You're trying to design a best 9-volt battery you can, right? But the thing is, normally, if you have something that has 9 volts, that's a certain amount of charge that makes that 9 volts, right? And if you put more charge, that will make it more than 9 volts. So what you want to do is something where you can put as much charge and much energy as you can, make it long-lasting, right? That's what all those commercials are for, right? Make it longer-lasting. But longer-lasting means it has more charge available, and more charge normally comes with more voltage. So you need something to hold down the voltage even as you put all that charge on. So that's what we have. If you have a really good dielectric, you can store more charge and more potential energy, make it longer-lasting, but hold down the voltage that would normally come with them, okay? So, that's kind of why you want to use dielectrics. Now, if you look at the equation for what goes into dielectrics, and I won't have time for this today, there are some catches. So we'll talk about some considerations for how you might build the best capacitor you possibly can, and it turns out that there are some situations where you can't win. You have to try to balance off what's good versus what's not. So I'll leave it there for today, and we'll come back to this formula and talk about how we can improve the performance of the capacitor next time. So we're not quite finished with our discussion about dielectrics. We finished last time talking about how we can improve the performance of a capacitor as a charge and energy storage device. Now we arrived at this final formula for capacitance. It turns out that we can improve the capacitance significantly by putting in a dielectric, an insulating material, kind of the filling of the sandwich, for the capacitor being the bread, okay? So, kappa is the dielectric constant of material, and if that's 2 or 3 or 1,000, you get that many factor times more the capacitance. Remember what ultimately, the mechanism by which it does that is that if you have charge on the plates, like so, then inserting that material will cause the insulator inside to charge polarize. It's going to suppress the electric field and therefore voltage. And ultimately, that means that we can put more charge on there for a given charging battery, okay? So that's the general gist of how that worked. And then we, of course, for a parallel plate capacitor, we can, of course, put in what is it that determines the capacitance in the first place. We learned that the plate area, the area of each plate and the plate separation determine the kind of baseline capacitance before you throw in the filling, throw in the dielectric. And so what I wanted to do today was carefully look at Each of these terms, there's three active ingredients, kappa, A, and D. Remember, epsilon naught is a constant, okay? So you have three different options to improve the capacitance, okay? The first of which is the dielectric. So we just talked about that. If you can find a better dielectric material, then you can get the capacitance to be better. So for instance, if you were able to find a material where, say, kappa is 10, that means that it can suppress the voltage and electric field by a factor of 10, so it's 1/10 its previous value, and that's great. Here you're ultimately limited by just materials that you can find. So, as you can probably guess, there's a certain upper limit if you just grab various insulators from nature and just throw them in, you try them out, see what they do. And if you don't like those, then you can imagine human beings have gotten around to tinkering and synthesizing materials specifically for this purpose. And of course, the larger kappa they can get, the better, right? So this is limited by materials. So you have to be able to find something that has this particular property or manufacture it. If we wanted to make the capacitance better, what should we do to the plate areas? We should make them bigger, okay? So that's another way to improve the capacitance. I guess I should put this over here because these are all things that are improving the capacitance. So here, they're limited by materials. Might there be a downside to making the area very big? What's the downside to that?
Too big to fit on a circuit board. Or
Too big, yeah. Well, you want to be carrying around with both hands, okay? So there's a certain size limitation. So the size limitations. Now, I'll tell you there's a trick that they sometimes use in capacitors to fit a very large amount of area into a small volume. Okay? So what they do is that they are not really parallel plates. One looks like this. This is a more advanced capacitor where the plates aren't symmetric, but the other one is like this. The surface area is tremendous, but they also pack it into a very small volume, right? There's lots of crinkles and folds. If you actually pulled it out straight, it would be a massive area, but it's crinkled into a very small space. These are your electrolytic capacitors. And this, with recent technology, has enabled you to have a 1 farad capacitor, which would normally be the size of a football field, and allow you to hold it in your hand. Okay? So a tremendous amount of area in a small volume. Now obviously that's a little bit beyond the scope of the course because the plates aren't symmetric. Occasionally we'll have you use an electrolytic capacitor in lab, and one of the things in the instructions is always make sure you connect it the right way, because the two plates aren't exactly the same, and which one goes to the higher voltage and which one goes to the lower matters. Okay. There's something you can do with area. Let's take a look at the final factor. Actually, are there any questions before I do that? Okay, so let's take a look at D. What should we do with the plate separation D to make the capacitor better? Decrease it. Now that one seems like a win-win. I mean, we make the capacitor smaller and we make it better, right? We bring the plates closer together and it's better. What's the downside to that? Well, as you can guess, everything has a downside. So that's when we get to something called dielectric breakdown. So, let me remind you of the relationship between E, the electric field, voltage, and plate separation. It looks like this. Now, in our previous discussion from last lecture, we had D as being fixed, And so therefore, we were looking at the electric field and voltage difference going together. So that's what allowed us to say, oh, if the insulating material, the dielectric, if it suppresses, it partially shields the electric field, then the voltage difference will also go down, right? But now, we're talking about messing around with D. So let's say we have V fixed, right? So let's say we have, for instance, V across the capacitor is fixed by a battery, right? But if we decrease D, what's going to happen to the electric field? It's going to increase. So the idea there is that the battery holds the voltage difference across the plates fixed, but if we bring these plates really close together, it's a precipitous drop of voltage from one place to another in a very short distance, right? We might have a 9-volt drop from here to here, very small distance, and of course, one of the things you hopefully learned in the electric field mapping lab is that if you have precipitous plunges in voltage, that means a very strong electric field. So, what's the big deal about the electric field being strong? Well, there's such a thing as too strong, okay? So, this is the time where we realize once again that the distinction between insulator and conductor is a fluid, continuous thing. Remember that these guys are just atoms that have been rotated because of the influence of the plates, right? In fact, rotated isn't really necessarily the best way to describe it. If you think of it like this, what is an atom normally? It's a positively charged nucleus surrounded pretty much symmetrically by electrons, right? Now you guys may know from chemistry that there are such a thing as polar molecules, right? Where the plus and minus aren't exactly concurrent. These things have a permanent dipole, right? They can be approximated as a plus or minus, kind of separate. But what we're doing here is when we apply the external field from the plates, E external, what we're doing is even if it doesn't have a permanent dipole moment, or permanent dipole, we are pulling the charges to one side. Not entirely, but of course on average, right, like that. So the negatives go upstream and the positives go downstream. This is what's called an induced dipole. You guys talk about this in chemistry? Okay, good. So here's what happens though. A little bit of this is good, because that's what gets you your partial shielding, right? A little bit of this means that now there's a plus over here and a minus over here, so there's your E induced, right? And that's what gets you your partial shielding. Partial shield. But there is going to be a point where these minuses not only get pulled upstream, they literally get yanked off of the thing, right? So we like our molecules to be stretchy, right? That's what gets us the partial shielding. But everything that stretches, you stretch it too far, it breaks, right? So that's what happens if you go too far. If this external electric field is too strong, these minuses don't just get pulled up here, they get pulled off, okay? If E external is too strong, it'll literally break that stuff apart. And suddenly you have a bunch of free electrons where there were no free electrons. You've turned bound electrons that belong to that nucleus, into up for grabs, right? And that's what we have is called dielectric breakdown. So dielectric breakdown is when the external electric field is so strong that it does not just charge polarize. So it does not only charge polarize and therefore partial shield, but it actually breaks the atoms and molecules in the dielectric or the insulator. So that's bad news, right? Because if the whole goal of the dielectric is to provide shielding, you've just broken those things, and now you have mobile charge, so minuses that are sitting next to the positive plate are literally going to be pulled off onto the positive plate and neutralize that charge, and vice versa with the other plate. So if you literally scissor, let's go like this, we scissor these, we kill these, then what we have is that there's going to be charge cancellation. And you've defeated the whole purpose of the capacitor. So, how do we quantify this? Well, every material, every dielectric material, it not only has a dielectric constant, which tells you about its ability to partial shield, it also has an upper limit. It has a dielectric strength. That is simply an electric field that is so strong that if you exceed that, you'll tear it apart. Okay? So, for every material, it has two values. It has a kappa, which is telling you about its ability to partial shield. If you don't tax it too much. And it also has a dielectric strength, or dielectric breakdown. It's just an electric field. So if you go on to the equation sheet, you look in the bottom corner there at page 1, you'll see a list of materials and you'll have two values for each one. The kappa value, which tells you about how well it functions as a dielectric, and the dielectric strength, which is the maximum electric field. If you exceed it, you will literally kill the ability of its partial shielding. You'll tear it apart and it will not be able to act as you want it to anymore. And of course, that's what we're in danger of if we make the plate separation too small. The electric field is going to go too large and exceed the dielectric strength. Okay? So if we go over here and we talk about what's the catch, kappa is limited by the materials, but this is also limited by the materials. So what you want to do is not go too small, such that the dielectric strength is exceeded. And you will find that when you buy capacitors at the store, they will tell you, do not try to plug this in above a certain voltage, because of course if you do that, you will zap the dielectric. And usually it's a permanent thing. Okay, this is not something where, oops, I'm going to unplug it and I'm going to use it again. This is a permanent tearing apart of the material, and you can't put it back together. Okay, so it's time to put in a new capacitor. So this is oftentimes, one of the things that goes wrong in electric circuits that requires repair is if you blow out a capacitor like this, you literally exceed the dielectric strength. Then there's a permanent damage to that material. You need to put in a new one. Okay. So to give you an example, one of the most common types of dielectric to look at is air, right? For air, just to give you an idea, the dielectric strength is 3 times 10 to the 6 newtons per coulomb, or of course, we learned equivalently volts per meter. So you might see this written as 3 megavolts per meter, right? Mega is 10 to the 6th. If you apply an electric field greater than that to air, you'll tear it apart. So one of the problems on your homework asks you to evaluate the dielectric breakdown in two circumstances, two very common everyday circumstances. One of which is walking up to a doorknob on a dry day and your finger zaps the doorknob. So that's dielectric breakdown. Your finger is serving as one plate of the capacitor, the doorknob as the other. And when the gap gets close enough, right, if you shrink the distance close enough, the electric field between you and your finger and the doorknob, it will exceed the dielectric strength of air, and you'll zap the air. You'll have a little spark that jumps. Okay? This is also what lightning is. Lightning is dielectric breakdown of air. So obviously it's happening over a much further distance. Okay? And that's of course because the charge involved in whatnot is a lot more. Okay? So chances are you do not have enough charge on your finger to jump from here to the next building, right? But you can jump a few millimeters from your finger to the doorknob, right? So I actually have you compute the exact numbers involved, and you'll find out they're both the same thing. They're both the dielectric breakdown of air, but why is it that you don't want to be hit by lightning, but you can easily withstand a shock from the little zap to the finger, okay? So that's dielectric breakdown. Are there any questions on that? Yeah.
So when there's dielectric breakdown, is there electric current going from one plate to the other plate?
That's exactly right, because anytime you have the mobility of charge, we can call that a current, right? Are there any other questions?